Hi, everybody. This is Giovanni and Steven. This is happy. You're still seeing me? I have some. Yeah, okay, good. I got frozen for a second. This is episode 22 of a show, The Physics of Bitcoin. We always make like a little introduction. Basically, the idea is that we discuss different topics that are related to science and physics and math, to analyze Bitcoin and its properties. Both Stephen and I, we have backgrounds in physics, in particular astrophysics, and we have applied this approach to different, not just to astrophysics, but other fields of knowledge. In my case, neuroscience. In the case of Stephen, computation. Different computational problems, and so the idea is that we think that physics can explain a lot of things in the world, in even social and financial systems like Bitcoin. And mostly our idea is around, our guide is around the power law, because it's really kind of framework that allows us to understand how Bitcoin works, but not necessarily we look at other ways of understanding Bitcoin scientifically. We also created this is an announcement. We will discuss it more in depth in the future, but we are in the process of creating an institute. It's going to be a research institute to actually spread this idea that Bitcoin it's a worthwhile subject for scientific investigation. In the future, it will be like a subject that will be taught in universities. People will spend, will have a research and maybe PhD thesis on Bitcoin, etc. So we want to start this process and have maybe other scientists coming and studying Bitcoin, different aspects. It can be mining, it can be anything that has to do with Bitcoin, but studied with data and scientifically, maybe the social impact of Bitcoin, many different things, economical. And we want to organize eventually conferences, that are focused on this scientific understanding. We are in the process of doing that. Anyway, by the way, happy new ATH to everybody. We had an amazing day today. We broke all-time high. So it's a moment of celebration, and this is great. Anyway, do you want to add anything? And by the way, I had everybody that is following me. I had a very fun day. I met Gladiator and his team that came to San Diego. We had a lot of fun. It was very interesting to meet young people that are so enthusiastic about Bitcoin. I'm very proud of them. Go ahead, Steve.
Yeah, well, I think it's a propitious day, breaking through the prior all-time intraday highs, and we're in both closing and intraday high situation right now. And it's what they say is that you don't have anything above you. You don't have resistance above you, so it could run for quite a while. I ran some quick log periodic models, by the way. And if you do a weekly model, it puts the critical day in the middle of November this year,
November, all the way to November.
which is a familiar month to you. That's
Yeah,
what
yeah,
you've
yeah,
been
yeah.
saying
I'm
forever.
going actually to run it. So this is what Stephen is talking about. Is this model that we mentioned many times? It's called log periodic power law. It doesn't have a direct connection with what we do, even if probably there is an indirect connection. But it's a method of finding oscillations in the price of any asset. It works with anything. In particular, it works very well with Bitcoin because of its nature. But it's basically telling us, given the current behavior, if there is any sign that we are close to some kind of a bubble, or maybe when you are at the bottom, if there is a bubble, or maybe there is a crash, if the market is ready for crashing. And what Stephen is telling us, that right now it looks very solid, and there is no sign that we are ready for some major corrections. And in fact, if there is a correction, it's going to be all the way in November. That is really cool. So we have several
Yeah.
months ahead of
We'll
us.
we'll have intermediate corrections,
Yeah,
but
yeah,
this is
yeah.
saying that, longer term. So if you run a daily for use 3 months a daily, then it says that there could be an intermediate correction in September. But if you look at the weekly for 1 year, it puts you out into November for the
Okay.
for the
So
the
maybe we
peak.
can we
Yeah,
can look at that next time. We can look at these because it
yeah.
will be interesting to check these results. Okay. So we usually start with Stephen presenting his agenda. He has a very well organized agenda usually, and he's actually, one of the I want to emphasize one of the good things about this show is that we almost every week come up with some new discoveries. It could be a minor or a major one, but it's something new that was never discovered about Bitcoin. And sometimes we talk about papers with other people discoveries that maybe the community is not aware of. So it's a really, I know that it's a little bit heavy sometimes in the math or in the concept, but I think it's a very good contribution because almost every week we add something new, some new ideas, some new concept. And I think at this time, Stephen has a very interesting result. So please, Stephen, go ahead.
Yeah, I'm feeling this may be more in the major side of things rather than the minor. The reason why we're able to do this is that because we have a firm foundation that we're basing these explorations on. And that's the foundation of the power law, but also understanding that we've got this distinction between bubble behavior and core behavior. So let me get into it. This week is all about difficulty, which of course is just hash rate averaged over uh, fortnightly intervals, 2016 blocks, strictly speaking. Okay, so this is Physics of Bitcoin number 22. And I didn't fix the title. Sorry about that. It should say difficulty. But here it is, the agenda, and it does say difficulty here. So the first thing I want to do is I want to apply a filter because I want to do the analysis from the time ASICs came in. Because originally you had CPUs and then GPUs, and there was a big shift in the underlying technology. So I'll talk about that.
And
And then
sorry,
I'll show
Stephen, if I interrupt you.
yeah.
Most people will know what difficulty is, but can you maybe define it for people who maybe
Yeah,
never heard
sorry.
it before?
Absolutely. Thank you. I should define that. So basically, all of the miners need to try many, many tests where they go through this double SHA-256 hashing computation in order to win the winner takes all lottery. And on average, somebody out of millions of these ASIC driven mining rigs, one rig with one computation will find the winning computation roughly every 10 minutes. Now, Satoshi understood that more miners were going to come on and there was Moore's law, the miners were going to get faster. And he understood that hash rate would grow quickly. And indeed, it is very steep. And so he had to introduce an adjustment. Otherwise, you would lose the synchronization on the network because the miners with new hardware or with additional hardware would find blocks faster and faster. And he wanted to keep a uniform block time of around 10 minutes. So he introduced this difficulty parameter, and it adjusts every couple of weeks, which is every 2016 blocks. So it can be more or less, but it's around a fortnight or 2 weeks. And that parameter tells you how hard you have to work to find the answer. Basically, you have to make a guess. It's called a nonce. You feed it through the algorithm. It's one way. You can't predict going in. You don't know till you run the algorithm. And then you have to reach a target, which is a very small number. You have to be below that. And that target is inversely lower as the difficulty goes up. And right now, the difficulty is measured in hundreds of trillions. It's a number a little over 100 trillion, but it's directly proportional to the average hash rate because it adjusts every 2016 blocks based on what the average hash rate was for all of those, that prior, 2016 block period. There's one little proviso there. It can't adjust by more than a factor of 4. for one adjustment or drop by more than a factor of 4 one adjustment, but it's going to catch up, within a couple of adjustments, and that rarely happens. So difficulty is, you can think of it as something that's proportional to average hash rate over a 2-week period on average. And then I look at the power law for that. It was really from 2013 on when the ASICs kicked in as the main mining rigs technology, and then the price versus difficulty history, and then this idea that price should be related to the square root of difficulty, or the difficulty should run something like the square of price. And this is something that Giovanni introduced several years ago. I may let you explain the reasoning behind that. You're better at that than I am. But then I'm going to look at a series of different correlations, and look at both the core and the bubble. And the correlations that I'm looking at are between the residuals of price, basically the delta in price in log terms relative to the power law trends. So the residuals in price, and also the residuals effectively in difficulty, which is the percentage change or the ratio of change at each adjustment for the difficulty parameter. And I've got actually 4 different kinds of tests, including correlations, Granger causality, cross correlations, and something called transfer entropy analysis. They all agree more or less. There's some differences, but the conclusion that I want to show to you today is that in the bubbles, difficulty leads price. More correctly, or strictly speaking, the difficulty adjustment leads the residuals in price. And then I have a hypothesis for why that could be the case. So let's get into it. First, the growth in difficulty has been very much beyond Moore's law. And, we started out in 2010 with hash rates of 5 to 10 mega hashes a second based on CPUs. And then a year later, people realized they should use GPUs, and they got factors of 10 to 100, kind of 30 at the high end. By switching to GPUs, a little more power was required. And then some people started using FPGA technology in 2012, and they got another boost of factor 2 or 3 from that. But the really huge boost came from custom designed ASICs specifically to solve the problem that I roughly described before. And that gave them a jump of, relative to GPUs, it gave them a jump of a couple of orders of magnitude, roughly.
And
And
again,
in fact,
maybe this is trivial for most people, but maybe for newcomers, with ASIC we mean people started actually to design chips that were doing one single task, right? And that task was to mine Bitcoin. And in this way, they made it very efficient. Is this a good way to describe what ASIC does?
yes, you can think of ASICs as putting software into the hardware, right? So directly implementing in hardware, custom hardware that's specific to the algorithm that you want to run, which is the double SHA-256 hashing algorithm. And it's a bunch of bit shifts and moduli, and it does per hash, it does hundreds of calculations, but they're all very small kinds of things, of shifting bits, some integer calculations, some moduli, that kind of thing, logical calculations. There's no floating point, for example. So the fact that this went up by 3 orders of magnitude with the technology shifts in 3 years, these are sort of quantum leaps. And so I don't want to distort my analysis by including them. So basically, I start all of this analysis 12 years ago from the middle of 2013, because that was the year that things shifted into ASICs. Okay, so we're trying to avoid that distortion. So having said that, we start from the middle of 2013, July 1st, and this is a log plot of difficulty versus Bitcoin age. And you can see it's a pretty good power law. We're still seeing on the left-hand side, we're still seeing some of that transition into ASICs, I think, happening. But at point 0.7, that corresponds to year 2014, and I've marked 2019, 2024 here as well. And the overall slope is 9.5, and the standard error is 0.36, and the R squared is very high at 0.94. So that's a hash rate growth of 6 orders of magnitude. 4 orders of magnitude came from hardware, and over a factor of 100 came from the increase in the number of mining rigs. So the number of mining rigs now is maybe roughly 5-6 million, something like that. You can sort of calculate, if I take the common faster machines, how many would it be? And it would be about probably, I think, 3 million now, but you allow for some older machines, it's more like 5 million. You go back to, the 2014 timeframe, you were in the tens of thousands. So it's increased dramatically. So this is a combination of both Moore's law type behavior of faster technology, and it was also started from a very kind of simple technology base. They've really been able to optimize over 10 years, and then adding, a factor of 100 more machines. Now you can then plot price versus difficulty as a power law, and Giovanni has done this in the past, and you find a slope of a half. It's not as nice a fit. The R squared is 0.84. The standard error is 0.35 in the slope, which is fairly large relative to the size of the slope. And but it's roughly difficulty goes as price squared, or price goes as difficulty, square root to the 1/2. Now, sometimes price runs faster and sometimes difficulty runs faster. You particularly notice after the 2013 peak, the difficulty ran up by a couple of orders of magnitude while price was heading down. In 2017, it ran up by, close to an order of magnitude while price was heading down on the downside of a bubble. By 2021, I think the miners had learned a little bit. And so, as the price fell, they didn't push the difficulty up as much as they had relatively in prior seasons. And then we also see a nice little upslope as we go into the end of 2024. What else do I want to comment here? I think that's it for this slide. Unless you want to say something about, Giovanni, about this kind of...
Yeah, I think this is a fundamental property, because my understanding, and it's a kind of one of these heuristic type of proof, and my way of thinking about this is that basically there are two things that the difficulty adjustment needs to compensate. One is, as the price goes up, you will see an increase in miners, right? Because they are attracted by the price. So you can say, in theory, it should be, as price goes up, hash rate or difficulty, they are related, should be proportional, linearly proportional. But if that was the case, then the miners will still gain by this increase in price, right? Keeping basically the same hash rate, they will still get more rewards because of the price. And the entire idea behind this difficulty adjustment is to keep things on the edge of profitability. So you have a little bit of profitability. It's still a good thing to do this mining, but you cannot basically take advantage of a system. You cannot exploit the system, because otherwise it will go in a runaway process, right? And so you need also to compensate for the price itself. And so this is why you have price square. So it's kind of one of these, we call it back of the envelope calculations, but it kind of makes sense that they should be related like that. Does it sound a good argument to you? Does it sound a good heuristic?
In general terms, and I have another slide on this that sheds a little more light, but the idea is that the miners are running close to break even, or maybe their margin is small, but they've got to compete with each other. So they're all competing with each other in a very brutal business for low margin, right? And the ones that are most efficient can hang on and grow. Okay, now this I call the difficulty chopsticks. I broke it down between bubble zone and core zone. And what you find is you actually get two different power laws, two different indices. In the bubble, the slope is 0.5, 0.47. But in the core, it's higher, it's 0.7. It also has a higher R squared, which is not surprising since, the bubble has more volatility than the core, which is not very high volatility. So in the core, price is going as something like the 2/3 power of difficulty. So, and overall, we see some kind of average. So this is just trying to elaborate this further, and I think requires some further investigation. It does actually hint at the conclusion I'm going to end up with, but it's not sufficient to draw that conclusion. This is your argument. You just made the argument about mining break even, energy per Bitcoin, Moore's law doubling, and so forth. But I would say one thing that you have to keep in mind with that argument is also the number of rigs is going up very dramatically. So that has some influence. Also, the ASIC slope for difficulty is 9.5, and the price slope for an ordinary least squares is about 5.7, and that ratio is 0.6. So that's another kind of power law index floating around within this whole argument. Okay, let's move on to the correlation studies. First thing I did was sort of sanity check my decision to start from 2013 for the analysis. So I looked at the price residuals from the power law, both positive and negative. So this is all of the data for ordinary least squares, and did a scatter plot against the difficulty adjustment ratio. So how much does it change from 2 weeks to the next? And the small chart in the middle, you can see it goes all the way up to 4, which is the maximum that's allowed. There's one data point that was over there. And it's got a pretty low correlation, 0.15. You don't see too much going on. It's pretty flat. However, if you just restrict yourself to data from the middle of 2013 on, the correlation increases from 0.15 to 0.4 very significantly. And here you've got a more tightly shown zone from 0.8 to 1.4. So mostly the difficulty adjustment ratio is upwards. Sometimes it's downwards. And you see this sort of scattering to the upper right of the chart, right? Which is when the price residual is positive and getting larger, and the difficulty adjustment is positive and getting larger. And those two look kind of correlated, right? And that's the core zone. So that's telling you something about the correlation between not in the core zone, in the bubble zone, about the correlation between the difficulty adjustment and the residuals in price.
In fact, you could use a cutoff, right? You could use a cutoff for that 1.1 difficulty adjustment ratio.
That's coming.
Yeah,
That's
okay.
coming.
All right.
Banding is coming. Okay, now I just divide by bubble and core. And so here it becomes more clear. All the core, the green ones below the line, the zero line for the residuals, all the bubble ones are above the line, and the bubble ones tend to have a lot more spreading over to the right-hand side of the chart. And also the sign of the correlation flips. So in the bubble zone, the correlation is plus 0.42. And in the core, it's minus 0.2. So that kind of suggests that there might be a difference in the way the lead and lag works. It's not conclusive, but it's kind of hinting at that. Okay, so then we look at the bands. And I divide it into four bands from zero point 0.9 to 1, from 1 to 1.1, and from 1.1 to 1.2, and then above 1.2 because there were not too many data points above 1.2. A couple of interesting things. First of all, the highest correlation is for the band from 1.1 to 1.2. And of course, this is only in the core. These are only the positive residuals. So in the core, there's very strong correlation if the difficulty jumps by more than 10%. However, if it's more than 20%, it actually anti-correlates. And that may be because you're overshooting the peak. And from 1 to 1.1, kind of more normal jumps, there's a weak correlation. It's a more normal market for a bubble market anyway, with mild upward adjustments. And then if it's zero point 0.9 to 1, you're in the core, but you're falling back in difficulty while you're in the core. The miners, maybe the market's so overextended and they're expecting a correction, or maybe you're on the downside of the bubble peak. Remember, this has both the bubble rises and the bubble falls within that zone. So that starts to be more interesting. And ChatGPT interpreted this as difficulty adjustments tend to amplify price deviations during the bubbles, but act as a damping force in normal core zone markets.
Yeah, and I like that, because I have this loop, right? I don't probably you saw it. It's one of my kind of central statements about how the different power laws interact, and it's a loop that I didn't create. In fact, it seems that Breedlove created that loop. He told me when he interviewed me, but I thought there was a missing piece, right? It shows all the interaction, like there is a drive in in value because Bitcoin, by creating Bitcoin and then people joining adoption creates value. Then there is the miners they join in because they look at the price going up, and then the miners creates more security that creates more people are more interested in Bitcoin in general. So it's a feedback loop. But I felt there was always something missing there, and I had as a secondary parallel loop the difficulty adjustment. And I thought this is a very important, I called it an inhibitory loop. I use these exact words. I say it works almost like because in many systems, like the brain, the muscles, they have these inhibitory systems, right, or loops that actually very, very important function. They damp too strong oscillations, right? There is one of their function. And it's a genius thing that difficulty adjustment was added. And it's also one of the things that differentiate Bitcoin from almost any other system, because Gold doesn't have it, Google doesn't have that, right? It really shows that there is something fundamentally different in how Bitcoin works, and is the difficulty adjustment. Very few people emphasize that. I added that as an inhibitory loop. It's almost essential. You want to have excitement, but you want to have inhibition. It's almost like the brake of a car. A car will not be able to work unless you have brakes. Sometimes you need to decelerate, right? Otherwise, you cannot go anywhere. So it's very important. Yeah,
Yeah.
I like that interpretation.
Yeah. And there are two ways in which that's necessary with respect to the synchronization across the network. So that's the temporal argument. And then there's the price and value side of things, right? You can't have exponential runaway price and have stability. And so you need it actually to control enthusiasm at some level. And when you put it all together, then you end up with a power law. Okay, so this is Granger causality, and you can check for both directions. You can check, do the price residuals lead the difficulty, or does the difficulty lead the price residuals? So now first, I check price leading or as the driver of difficulty adjustment, but I divide it into the core zone and the bubble zone. The red line is the bubble zone. And so what we see is, for the most part, price does not lead the difficulty in the bubble zone, because on this graph, you want to be low on the graph. This dashed line is at probability 0.05, and that's the level at which you think things are significant, because the way they do this is they're rejecting a null hypothesis. So if you're at 0.05, you actually have 95% confidence in what you're looking for. And so in this case, price is strongly leading difficulty adjustment in the core, and that's the green line, and particularly at around 4 weeks, where the p-value drops to less than 1 part in 1,000, about 0.0004. So that is a very strong relationship, and it's good, in the interval from 2 weeks, where it's at 2%, out to 8 weeks, but kind of peaking around 4 or 5 weeks. And for the bubble zone, it has a little bit of predictive power, but just at 2 weeks. But that fails as you go to longer time intervals. So that's how you interpret that. Now, we're going to flip it, and we're going to look at difficulty adjustment leading price residuals. And the chart flips. Now the green line is right at the top, all the way across. It's basically saying there's no causal effect. Difficulty adjustment's not leading in the core zone. It's not leading price, right? So this is kind of our common understanding, is the price leads difficulty in the core zone. But in the bubble zone, the Granger causality is quite good. There's the dashed line at 0.05 in the middle of the plot. And you see, again, at 4 weeks is where the peak is, where the red curve is the lowest. And that value is less than 0.01. It's about 0.002. And it rises up to 0.006 at 6 weeks. And it's even significant at 2 weeks. So, again, in the 4 to 5 week kind of range, it's quite strong. The difficulty adjustments are leading the price residuals in the bubble zone. And this is a broadly defined bubble zone, because we're not using the 40-60 bands. We're just using the 50 percentile band in quantile regression terms, or in this case, we're using ordinary least squares. And then you see the other one is shown, the small graph is the other one. So you can see how it flips around. Okay, so that's one test. Here's another test. And these tests for kind of different things, but collectively you can kind of search the whole space, because some assume linearity, some don't. These two tend to assume some sort of linear relationship, at least between these logarithmically defined residuals and ratio defined liquidity. And this is looking, the way this works is, on the right-hand side, difficulty is leading the price residuals. On the left-hand side, it's the opposite of that, because that's negative lag. And again, we see confirmation of the difficulty leading residuals, but here, and it's pretty good results, because it's levels like 0.04, 0.05, and above 0.05. It actually doesn't peak till 10 weeks. So in the bubble zone, the highest cross correlation is difficulty leading, not price, and maximizes at 10 weeks. Now, I also tested this by running 1,000 trials of shuffling the difficulty adjustments, and that produces the gray band at the bottom. So what we're saying is, we could not get this by random behavior. 950 of the 1,000 trials are in that gray band. So this is not random behavior. So the idea is that miners are responding to early price strengths, and their increasing difficulty further amplifies market enthusiasm, And there's some feedback loop. It takes time to propagate, and the strongest impact is 10 weeks later.
So what happens? You think that people see that there is a lot of activity in terms of hash rate, and they interpret that as bullish signals, and then there is some kind of amplification mechanism like that. Is this the
No,
interpretation?
no, that's not my interpretation. My
Okay.
interpretation is that the miners are smart money.
Okay.
That the miners,
Yeah.
the ones who have been successful,
Yes.
need to run their businesses. And so they've got eyes on their businesses 24/7.
Uh-huh.
And they're very, very sensitive to price, right?
Right.
And so they are monitoring signals for price. They're
Mm-hmm.
monitoring liquidity, for
Uh-huh.
example.
Uh-huh.
They're monitoring anything else they think is a predictor of price. They have to, as a function of their business.
Right, right.
They have to
They
make
have, they have, they
decisions.
have some unknown alpha, and they start to
Mhm.
improve their production. They decide, okay, it's time to increase, and
Yes.
okay, and this is what is happening. Okay, so we
Yeah.
actually can learn from them. We can
Yes.
use this as a leading signal. Okay,
I think of
makes sense.
them as whales.
Hmm.
We've shown that the whales, or Sornet has shown that the whales are smart money, right?
Okay,
These
so
guys are smart money.
Mark Kaisers is very strong on this, right? He makes it a very general statement that hash rate always leads, but it what we are saying is looks like it's right, but only for the bubbles. Is this
Right,
okay? Not
right.
not when we are not in a bubble, but when we are in a bubble, yes.
Yes. Okay. Now, there's another way to do this is called transfer entropy, comes from information theory. We're asking the same question: does difficulty help predict price? And that box in the upper right-hand corner shows a little bit of the math, but the basic idea is if X is the difficulty ratio and Y is the price residual, then can you get a better prediction by adding difficulty into the mix as opposed to just having price try to predict itself? It's kind of conditional additional information is the idea
Hmm.
without going through the messiness of it. And this slide shows a 1 period lag, which would be actually a lead, would be where difficulty is 1 period uh, ahead of the price is lagging by 1 difficulty period or 2 weeks. So what you find is in the bubble, the transfer entropy number is 0.058. In the core, it's 0.015. So it's 4 times higher in the bubble. And there is a way to interpret this. And you look at this transfer entropy value, and then you look at this chart on the right in the middle, and you look that up. You say 0.058. Well, that's in this range, 0.03 to 0.07. It's somewhat at the upper end of that, and it says moderate influence. And if it were 0.07, it would be strong influence. So we're seeing about 0.06. You can measure this in what's called nats, which is like a number of logarithmic units or bits. And we're measuring in these nats, but that doesn't matter. It's this value and how it fits into this grid. So it looks like a decent, higher end, moderate influence, almost strong influence. And that's for just the lag of 1 difficulty adjustment. But we can look at this for different lags as well and see how it changes as a function of lag. So
Can,
that's
can you can you actually make a model of a price based on this?
um,
So what, for example, if you get decent difficulty adjustment, what that predicts in terms of a future price?
yeah, I have a couple of guidelines that I'll show, but I don't have a model at this yet.
But maybe we could work on that, right?
It's something to think about.
Yeah.
Yeah. Let me show you the guidelines, which are kind of a trigger type thing.
Okay.
Okay, now here is different lags. So this is difficulty leading residuals. And this is the entropy value as a function of that. It's pretty flat. It's about 0.06 from 2 to 8 weeks. And it's almost up at that 0.07, strong influence level, but it's at the high end of the moderate influence. And our highest value is 0.06 something. So it's pushing the upper end of that moderate influence. I'm going the wrong way, sorry. Okay, so those are the different analyses, the 3 or 4 different types there. And the 2 keys to this, and the reason why we're able to tease out this relationship are, 1, that we use residuals from the power law, log price residuals from the power law. And 2, we separate the core and bubble zones. And that's when we really start learning some new things. So what you want to do, is look for difficulty adjustment or hash rate growth that's larger than usual in percentage terms, that's above trend. And this shows that the 3 methods agree. So their correlation was the banded thing, the Pearson correlation. Then we had the Granger causality, and we had the transfer entropy. 2 of them detect nonlinear behavior, and a couple are lag aware. Linearity is assumed for correlation, but somewhat Granger can detect nonlinear. So they kind of cover the map between all of them, and they're all giving broadly similar results. So the conclusion is the finding's solid. Bitcoin difficulty adjustments lead power law residuals by 1 month or more in bubble regimes. So what we want to check is difficulty above trend. So let's look for the last several periods. I show here the difficulty change for 1 month, 3 months, 6, and 12, and then change that to per month averages. And what we see is it's grown at 3% over the past 12 months, but over the past 3 months, it's only grown at 2%. So we haven't seen a difficulty change recently. And over the long term, you'd expect with a 9.5 power law, if that's holding up, you'd expect 4.8% per month. So we're not at that level now. You also want to look for a single adjustment that's higher than 1.1, because that's where you got the highest correlation of 0.44. This shows all of the difficulty adjustments since Halloween last year. And we have the highest one was recently, it was in April at 1.07. So we're starting to get close to that, but then we were flat for the last couple of adjustments after that. Or close to flat. We actually had a down adjustment for the last one. We're due for another one, which should be up. So I think this is not a model, but it's, kind of looking for indicator so that one could start thinking about.
Right.
Okay. Now, here's some hypothesis from ChatGPT on the left and from myself on the right. This is supporting miners as early responders. During bubbles, miners may ramp up quickly in response to market signals or liquidity. So somehow they're detecting signals like, maybe it's something simple like the second derivative is moving up, right? And then difficulty becomes the leading indicator of increased interest and forthcoming price spikes. And you also get a feedback loop. You get this positive feedback between hash rate and difficulty, and investor behavior and price deviations can grow stronger. And then it makes the point about the thermalized core. In the anti-bubble or core zones, the market is less reactive, more equilibrium and mean reverting. We know that from other discussion. So my speculative hypothesis here is that liquidity and maybe some other signals are leading miners by about 6 weeks. Miners are picking up on that, and they start increasing their difficulty and their hash rate. Well, they start increasing their hash rate, and that drives up the overall difficulty parameter 2 weeks after that. And 6 to 7 weeks, the bulk of the momentum traders start figuring things out. And that gives you the lag between liquidity and the price more broadly is something like 11 to 13 weeks. So in conclusion and summarizing, in the ASIC era, difficulty rose is the 9.5 power of the age. Price versus difficulty is an overall square root index, but the bubbles, it's different than the core. The core is higher at 0.7. Difficulty can keep rising as the bubbles pop, although that seems to be coming down a bit as the miners get a little more sensitive to that. Price leads difficulty in the core. It's strongly Granger causal at 4 weeks. Difficulty leads price in the bubbles, larger and positive residuals. There's a positive correlation if you're in the band from 1.0 to 1.2 is the difficulty ratio adjustment. Cross correlation at 10 weeks, Granger casual at 4 weeks, transfer entropy 3 to 4 times what you see otherwise with difficulty leading in the bubble zone relative to the core zone, and it's strongest at 6 weeks. So overall, you look at these, one says 4 weeks, one says 10 weeks, one says 6 weeks. The middle of all that is something like 6 or 7 weeks, perhaps. So you want to look for 5% per month growth in hash rate and difficulty, and you want to look all at once for a difficulty adjustment above 10%. There's a couple of potential indicators. Okay.
Is there any way to use these to know when a peak has been reached? Do you see, is there a way of knowing that actually things are changing and the miners are pulling out of they are decreasing hash rate or something? Did you study that?
There's a hint. There's a hint from our bands. So when you, if you get a difficulty ratio jump of 1.2, the miners are getting over optimistic, it seems. Even the miners are getting caught up. And so extreme difficulty jumps anti-correlate with price.
Okay. So that actually could be a sign that maybe the market is overeating. And
it's an overshoot.
Yeah.
Now, I want to redo all this analysis and just take a 5-year window because I'm concerned that most of these large difficulty adjustment ratios were in the earlier portion of that 12-year period.
Right. But very, very, very interesting. Yeah.
Okay.
Very good.
I will close out there.
Okay. All right. And I will share my slides. And later we can check if there is any questions about these. Hopefully there are good questions. Okay, so I'm sharing this. Okay, and I'm going here. Yeah, so I have a couple of things I want to discuss. Let me see if I can make these. I always try and I fail. It will continue to be a source of entertainment for the viewers because I'm always trying to shove a slideshow, but it never works. Oh. It should start from here. Did it change anything? I don't think it changed anything.
It did not.
Yeah. All right. We will still focus on this. Okay. So what I did, I look at Google searches for Bitcoin, for the term Bitcoin. And they have some kind of an index, right? It's no, I don't know if I don't find the right thing. I guess I was expecting number of searches, but they have some kind of an index from 0 to 100. that is supposed to be some kind of showing the proportions of the searches, and this is why on the x-axis you have from nothing to 100. That is the highest possible index. And so I plotted it in a log chart. And people that are familiar with the idea of power laws, they know that if you see something that is somehow straight, like a straight line, right, to kind of linearize, you will never see something that looks like a perfect straight line. Data has always some kind of level, some noise, right? So you see maybe a fuzzy straight line. That is what you're seeing here. So I had this intuition that it will be some kind of a power law, and I was right? So it does look like a power law. So this is the price, this is the searches, and is linearized, and you can fit a line. And the R square is not super amazing, but it's good enough. Like, believe me, there are many. Like when, for example, I was in neuroscience, we saw anything like this will for sure be a publication. Even like Stephen was talking about correlation of 0.45. They are good, strong correlation. This one is 0.75. Now, the one that we are used to, like the power law in time, that is 0.95, is almost like physics like. It's really incredible. This one is pretty solid. If you're thinking that is, probably even this index is kind of approximated. Anyway, these are monthly searches, so there is some error there, but it's quite amazing, that there is such a strong correlation, and it's a power law. And the slope turns out, it also depends how you measure it. Here I quoted 0.8 times. I think I was going by memory, so let me correct it. I should not report fake information. Okay, it's more like 0.75. But the slope is 1.95. That is interesting because it's very similar to what we find between addresses and price. And so probably there is some very strong reasons why we see this square. I gave actually a proof, like a theoretical proof. I think I did it one in our episode. I went through the proof, something about you expect some proportionality, and that you start with that is your basis, and then you're saying, well, this proportionality will be based on some kind of level of activity or interest, but not everybody will do something of that interest. In this case, it's difficult to say, is it the price that creates the interest, or maybe the interest is affecting the price, right? Like maybe, I think it's a feedback loop, right? These things never go just in one direction. But there be, people, maybe they can check Bitcoin very quickly out, and then don't do anything about that. Other people will be obsessed about that and check many times, or maybe buy Bitcoin because of this interest. So the level of activity, it's following one of these Zipf's law. That means, some people will be very active, like a small percentage, 20%, and my majority will not be very active. And by just assuming these two things, that there is some kind of direct proportionality between the price and the level of interest, and then that the level of interest is not uniform, but is going to follow some kind of distribution. Like we see that this distribution in income, we see this distribution in how people are active on social media, in a club, it's basically a power law. Also, that is a power law, but in this case, is the distribution, right? The power law will be inversely proportional, where the y-axis is the number of people that show a certain level of activity, and the x-axis is the level of activity. That means there'll be a lot of people that don't do almost anything, very low level of activities, large number of people that don't do almost anything. And then there is a core of people that produce a lot of activity, that are the most they most active on social networks or in a club or in an organization. They drive most of what is happening. And if you have a distribution like that, you combine the two. I show the math in last episodes. You get a power law, and y squared. I'm not sure. That proof just tell us that you should get a power law. Uh, Maybe there is something fundamental. It's one of these things that I'm still trying to figure out. Y square. Now, square, for example, if you relate it to Metcalf, you get it if you have a network where everybody's connected with everybody else. Um, the number of nodes in that network will be square. So maybe the two are kind of related in that way. The other thing that I would love to know one of these days is why a lot of these networks, when you look at the growth in time, it's a cube. Like viruses, some viruses grow like a cube, and Bitcoin grows like a cube in time. The adoption of Bitcoin, the number of users grow as a cube. And they found, maybe we discussed this in another episode, I found an article recently that was describing the growth of networks that are very old, like 100 of years. One is um, the collection of reviews about movies, and that grows also with a cube. And what and the internet, most of its history actually was a power law. Many people quote the internet as being an S curve, but it's really actually a power law, and now it's tapering off. But that power law is close to 3. So these are some of the numbers that I would like to understand why this is happening like that. What that 3 means or what this 2 means. But anyway, so this is a model. So if you take that, if you take these, right, it's really interesting. Right? You can take these. These are all these dots that seem random, and then you make a model where you say, okay, I'm going to take the slope from these. I'm going to take the y-intercept, and then I'm going to say, okay, the price is equal to searches to the square, right, 1.95, and you use the y-intercept for the model. This is the model that you get from that, right? So the red curve is the model, the black curve is the real price. And you see, it's a pretty good match. It's interesting to see a few things. It seems that during the bubble, actually the model overshoots. So it seems that everybody gets, if it is kind of, it makes sense, right? Because this is the peak of a FOMO. So if you had to calculate what was the price based on all the interest and all the craziness going on, the number of searches, you will overestimate. But it's really the definition of FOMO is exactly what you would expect when there is FOMO, right? So that is really interesting. And the other thing is this, where the model seems to be worse. It was pretty good match beside this overshooting, but now it's deviating. And one possible explanation, I don't know what to say that, and people comment on that, right? I saw several posts, people saying, "Oh, we are reaching all-time highs, and Google interest looks almost like flat." Um, it could be one possible explanation, right? Maybe there are other social explanation, like people are not involved anymore. Right? Here, maybe they were involved because they felt that they could join in, because psychologically the price was still affordable. So maybe it could be one explanation. Um, and now it's like this crazy price, and people think, I don't care. I cannot buy. They think that you have to spend really literally $100,000 to buy one Bitcoin. Some people have very strange ideas about that. Or it's psychologically too far from what they think is affordable. Or the other could be that people are using other search mechanisms, like ChatGPT or Google, Grok. They don't use as much as before Google. So I don't know. I don't know how to interpret this. What do you think, Stephen?
Well, I think the Google numbers are just relative to itself. So I'm not sure that the fact that people are using chat or grok is explanatory for that.
Mm,
Another possibility is you're just seeing the left hand side of a bubble yet to come, right?
right.
So, and that sort of depends on how far this bubble goes, whether that explanation would make sense at all. By the way, I
Okay.
have a comment on the square law relationship.
Yeah.
I think what happens there is some people who are a little bit earlier do Google search, and the people who are more into the Bitcoin market and participating at higher volume, uh, talk to their friends, right? And they say, look, the price has gone up. And then their friend goes and does a Google search. So that is going to give you Metcalfe's law kind of behavior. They just send a
Mhm.
message to their friend, right?
Right, right, right.
And then their friend does a Google search.
Yeah.
So that's going to give you an n squared effect.
But I thought that will maybe give you more of like a power law in general. Why square per se?
Because people talking to each other is a Metcalfe's law. People sending
Right.
messages to each other is just a messaging network that
Yeah, yeah,
goes as a square. Now, I think a problem here is, as you said in the beginning, this thing is normalized, to go from 0 to 100, right?
right.
So how do you correct for the fact that it's got this saturation in there, and you don't even know what their algorithm is? You don't know
Yeah,
whether they're just taking I think what they do is they just take the prior 5 years, and then they say, what was the peak? And that's 100, and everything's relative to that. So, there needs to be some correction for that
you
as
know,
well.
it's still amazing that we get this strong correlation between the two, right? It's very interesting. It does show that there are very strong network effects in
Right.
the price of Bitcoin.
But
Um,
it's
yeah.
not going to run up to 100 until we're right at the top of a bubble, right? So,
Right.
yeah.
Anyway, the next thing I did was this exploration of because many people say, well, why you call it a law? So it's a law because really there are this proportionality between the scale of time and the scale of price. It's what is called a scaling law. It's really something about mechanism. This is why a law, right? Physics law has to do what causes, what causation. That is one of the things that different from biology, right? A lot of biology try to describe things as they are. Now, for sure, many times they are trying to find a causal link, but in physics, it's even stronger, right? We really care about why this is happening. What is the causal link? What causes these particular phenomena? And and if you have something as powerful as this scaling property between two quantities, there are mechanisms that produce that. It's not something that you can get by chance. And many times laws in physics are related to symmetries. Like almost all the physics law can be derived from symmetries. There is actually a beautiful theorem. It's called Noether's theorem. This woman physicist found this beautiful correlated, pattern between different type of symmetries and the most fundamental laws of the universe, in particular conservation laws. Like for example, you can show that uh, the fact that a lot of laws are symmetric in time. Basically, you can look at the planets and they move in a, like if you show the movie of how the planets move, I can show you the movie backwards, and you will not be able to tell if you didn't know exactly how the planets move. Also, because you can look at from one direction or the other direction, in the solar system, up, downwards or upwards. You will not know. You will not know if a movie is run forward or backwards. So it's symmetric in time. Now there are certain laws of physics that are not symmetric. Like if I show you an egg falling down towards the ground and you see the egg breaking, if I show you the movie backwards, you will see that there is something weird. If a egg goes back together, from being broken to be whole, say, you're running the movie backwards. But That is an exception versus, the general idea that most laws of physics are symmetric in time. And you can show that this symmetry in time leads to conservation of energy. That is one of the most fundamental principle in nature. And, the fact that you have symmetry in rotation. The laws of physics also look similar when I rotate an object, etc. This leads to angular momentum. The fact that the laws of physics are similar when you shift from one place, like in a linear fashion, to another place in the universe, this leads to conservation of momentum, that are all fundamental laws of physics. And so we look for symmetry as one of a way to tell there is something deep in some kind of a phenomena that we study in physics. And hold and behold, in Bitcoin, there is a symmetry. And this symmetry, it's related to the power law. It comes from the power law. But you can start from that. You can say, I want to test a symmetry. And this symmetry is where you stretch time. And this is what I'm trying to show here mathematically. Basically, I'm taking time and I'm stretching it. This lambda, this factor, is a stretching or a squeezing. So imagine I'm saying I'm comparing what Bitcoin did at day 100 and day 350. And, in this case, I basically stretch time by a factor of 3.5, right? And they get 350. And I want to see what happens to price. And if there is some kind of transformation that keeps the system symmetric, that makes it look still like a power law. So I do this transformation, I change the time. It's called time dilation. And you can also squeeze it. You can start from farther time, like today, and then check what the price was 200 days ago or whatever, at any time. This lambda represent squeezing or a stretching. And the power law suggests that there is this transformation where you go from, I'm going from a time to a time where there is some kind of a constant. And here the same thing happened with price. I go from the price, let's say 100 days ago, to the price now. This lambda represent 100 days stretch in time. The new price will be nothing else than the price now multiply by this stretching, so whatever it is, 2 times, 3 times, let's say it's 2 times, times to the exponent alpha, where alpha is, the exponent that we are familiar with the power law, that is 5.8 or whatever, right? So this is called a scaling transformation. So I want to test if this is true. This is a symmetry, because what happens, I think about this, right? So I'm moving along the power law in the x-axis, and I want to see where I end up on the y-axis. If I end up on the power law, right? So basically the power law is still looking like a power law, then it's a symmetry. The power law is not, and symmetry means you do something, you do a transformation, and you get back what you have. Like the circle is very symmetric object because you can rotate it in every direction. The circle still looks like a circle, right? A triangle has, like an equilateral triangle, has certain symmetry because I can do certain rotation that brings back the triangle to itself, right? It's less symmetric than a circle, but it has some level of symmetries. And there are many types of transformation. You can take a square and flip it, it will look like itself, right? That is a symmetry along the axis, etc. In this case, we are trying to do a transformation along the t-axis, where we change the time, we double the time, triple the time, and we want to see what happened to the price. Do we get a symmetry? So this is what I did, and I did it many, many times, over and over again. So basically what I'm doing, this is a test where I pick a random time, I check the price that is predicted by that transformation. I'm applying that law. I'm basically taking, so let's say I take a time that is 3 times bigger, right? These times are always in terms of how long Bitcoin has existed, because this is a relevant time for us. So Bitcoin was 100 days old when I check in 350 days old, 3.5, right? That will be the lambda. And I'm expecting the price to be 3.5 to 5.8. And I'm checking over and over the predictive value relatively to the real value. So here on the y-axis, I have a predictive value. Here I have a real value. And if they are similar, they should follow, right? There will be some noise because we know that there are the bubbles, even the core has some noise. It's not going to be perfect. So I'm testing it over and over and over. Now notice that if I go below $1, the data that we had was not very good. Markets were not still open. There is some kind of, I use data that contains a lot of noise. But even this data, they kind of align along this line. And then you see after $1, right? This is basically $1, $30, 900, right? They match, right? Because in average, you get that we are predicting very well that this little formula that we are using, it's a very good predictor in average of the price of Bitcoin. And if you are interested then in calculating the error, right? So you say, okay, I want to see the distribution of these errors, right? The error in this case will be the predicted minus the real divided by the predicted, right? And you can calculate how big the percentage error, and this is the distribution based you're counting how many of these errors you have in this range, right? Between, let's say, minus 100, in this case, will be you're off by a factor of 2, right? And then the next bean, you divide these in like little beans. You're checking the error between this range and this range, and then you count how many you got, right? I think I did a test with thousands of trials, and then you get this distribution. You can see that is exactly what we have described many times, that there are basically two modes for Bitcoin. One is this core mode, that is this one, where basically the most likely value. So when people say, oh, I probably should color code it, where I show you the bubbles and the core. They say, oh, the power law, it's all over the place. It's not, because during the core, we are basically confined to this range. It's very, very collimated, right? It's actually, remember, this is what we call the reference power law, right? It is kind of a middle ground between the bubble and the support level. And while this is the support level, so we have shown this many times in other ways, that most of the time when we are in the core, we are somewhere in between this reference line and the support. And this is showing exactly that. And it's very collimated. It's very narrow band around that. And Stephen has shown this. This is very similar to his model, where he has basically two Gaussian that are describing these distributions, right? Now, this doesn't look very much Gaussian, probably more log normal. So it has a very, very long tail. But again, in that case, we are coming very close to that reference point, that equation that we just showed, is where you get this peak, right? So the error is very close to 0 in that case. And then you have, you do have some counts and some values that they can go all the way to even 3 times the value that the formula predicts. But you can see as you go farther and farther away from the predicted value, these are not many counts. It's like rare situations where we go far away from the prediction. So it can happen, but statistically it's very rare. So you can see it's very, very, very good model, right? It's a very good predictive model of what happens with Bitcoin. So I was very happy to do it in this way, because it's just another way of showing how good the power law is. In average, it gives you a very good feeling. If you do it over and over again, it tells you what the price should be. And again, something like this, you don't get it by chance, right? It has to be that there is a real physical behavior of Bitcoin that makes it behave in this way, in this scale proportional way. So this is one of the tests that I did recently with so it's another scale invariance test. I think it's very interesting. Do you have any comments about this, Stephen? Or anything you want to add?
No, it makes complete sense. Yeah.
Yeah, this is very similar to
Yeah.
what we found,
Yeah.
right? In
Yeah.
using different, like measuring the residuals in that case from the power law formula. Yeah, then I apply all these to actually this model. So um, he showed something similar like this before, right? That you can fit the residuals. So in this case, it's not the error due to this transformation, but it's something related to that, where you take the power law equation, the usual form of equation, and then you calculate the differences from the model, and you get distribution. That for somebody that is used to see this distribution, it's kind of obvious that there are two modes. Uh, and so you use what is called a mixed model. When you did yours, did you have a three Gaussian, or did you also model the intersection between these two, Stephen, or just
Uh,
two?
I modeled. Yeah. No, it was a Gaussian mixture with two.
Two.
Actually, they're log normal because it was done with the log residuals. Yeah.
Okay.
Yeah.
Yes, exactly. So you take the log residual, like actually I do
Yeah.
here, and then you fit Gaussian. So actually that assumes log normal. Log normal means that the distribution is not normal, or normal. It's another way to call the bell curve, right? That it is, you're expecting kind of a symmetry between the center, that is the most likely value. But many distribution in natures are not like that. We have this long tail. But you know what? When you take the log of this quantity, then they do became Gaussian again. They became again bird curve. So this is what you do. You take the log of a residual, and then it looks like you have two instead of one for the bubble and one for the core, and these are the two distribution. And then what they did, you run this code that assign weights to these two distributions, and then it calculates the quantile taking in consideration this Gaussian, this mixed model with two Gaussians. And I also introduce a decay of the peaks. So this is an elaboration of a quantile model that contains this Gaussian mixture plus decay of the peaks. And I got this. So it should be a little bit better than the usual way of doing the quantile model. And it's using this idea that we are actually dealing with two modes instead of only one, the core plus the deviations when we are not in the core. So this is some of the work I did recently, and I wanted to share with you. And any question about this? Do you agree with this approach, Stephen?
Fully, fully agree.
Okay.
Yeah.
And that's really cool because in this
Mm.
graph, I'm going to use this to make updates in my X account. I'm also showing with a star where we are. This is not the
Mhm.
latest update. I'm going to do the
Mhm.
latest update in maybe tomorrow. But it's cool because then the star tells
Mm.
you where we are in the distribution, right? Because of course, right now we are still, at least until a few days ago, we are still very close to the power law, because 0 0 will be basically the power law. And as the star starts to move farther and farther away, you can see that that is probably not sustainable, right? It's probably will be a correction, and the star goes back to the core, right? Or at least the upper of these deviations, where you are expecting maybe, because you see, for the core, sorry, for the bubble, zero point 0.5 is the most likely value, right? So right now, actually, there is room for us to go there. And if we deviate, probably, there'll be a correction, because most of the time, even during the bubble, we don't spend a lot of time at the peak. We spend most of our time here at zero point 0.5. So it's a way of telling, are we overpriced? Are we underpriced? Right now, we are kind of, if we are in a bubble, indeed, this is the relevant distribution. So we have room to grow, right? Even just to go to the middle. So in fact, I calculate the middle right now, it's more like 130. So during the bubble, if we spend, the next 5 6 months in the bubble, we should go closer to 130. And then
Right.
very, very little time will spend here at these extremes. And check these streams, it's consistent with the 200K that I
Uh,
mentioned times.
Giovanni, where is your point 0.6 quantile level right now?
In my 0.6 quantile level, it's like
Yeah,
the first line. So in the table, the
yeah.
six, this was calculated a few days ago. It's 96 in this model
Point
because
0.6 is 96.
yeah, because it has also
Wow.
a decay. It has also a decay.
Yeah, yeah.
Yeah,
Okay. Well, I'm just trying to figure, whether we have broken out of the transition zone. I'd like,
barely, barely.
yeah,
Yeah.
I'd like to see us get to 40 ounces of gold, which would, is a little higher. It's like 130.
Yeah. So
Um,
the fact
yeah,
it's barely is actually good news, right? Because it says that we have room to grow.
for
That
sure.
yeah, we
Yeah.
can go all the way to 130, and that will be actually just normal for being in a bubble. And then the interpretation of that long tail is that if we go to a bubble, we will stay there for a very short amount. Maybe we go to 200 and then there will be a correction. We are not going to stay there forever. Now, this again, all based on Bitcoin doing all the things that it did before in the past. It is the only scientific way to analyze this, because what else can you do? You cannot, if he does something else, we don't know. All what we can do is say, okay, if it behave like in the past, then this is what to expect. And it's also good because if it does something different, let's say it starts to, many people talk about this extended, long cycle, that I don't believe in it, but whatever Bitcoin does, it does. If it does, these models are still useful because it will show that something is different, right? It's a way of actually detecting that Bitcoin is doing something different. So they are still useful even when they don't work. Modeling is still useful even when you see something different, because it's a way to compare the past with the present. So it's still useful to do these models. Anyway, you guys do you want to take some question? Let's see which question, if we have any questions. Okay. I don't know. I don't know how to read this, understand this question. Do you understand this? Could add to the agenda Coinbase Premium?
I don't know.
Yeah, you don't understand this too. Um, okay, this was a funny comment. Yes, it's yeah, it was fun. It was a fun day. I like. I'm a teacher. I love young people. I love this enthusiasm we have for Bitcoin. So I'm all for it. Um, okay. Okay, it says, thank you, Giovanni. I will have sold when Bitcoin fell at 70 a few weeks ago, but held because my conviction with power law. Yeah, that is, you should never take anything like this as a financial advising, um, advice. But this is why we do these things, because even for us, right, it's a kind of a guide. It tell us, to me, once we started to discover these patterns, I feel much more serene, because I look at this pattern, I see where we are and trying to understand it. I trust Bitcoin, and I know that Bitcoin has some wisdom, and it tells me to identify where we are. Are we overheated? Are we not overheated? Are we close to the bottom? I did call the bottoms, and again, it has nothing to do with me. I found this pattern, and there was pointing out to people, look, it looks like we never went below this. I have a Facebook post, I was mostly active on Facebook, where I say, guys, we reached the bottom. We never went below this value in all the history of Bitcoin. I think Bitcoin does things in a very regular fashion. Do what you want with this information. And many people were making fun of me. Sure, we are going to nothing, whatever. And it turned out it was not, right? People could have acted on that information. You need to study Bitcoin. When people say study Bitcoin, there are many things you want to study about Bitcoin, right? All the other non-price related aspects of Bitcoin, but price and understanding this other thing, how hash rate is working, how addresses are working, give us valuable information. And then you can do, of course, in the end, it's you that makes the decision. We cannot tell you do this or this other, but this is why we do this, because I think there is valuable information in this analysis. Okay. So here, this comment: the miners kicking on the extra miners. They're trying to front run. Is this?
Yes, and indeed, I agree with that. And sometimes they may have some older miners that were not profitable or marginal, and they may turn those on as well. But I certainly agree with this. That's what they're doing. They're trying to front run their competition and the anticipated price increase.
Yeah, and he's elaborating, saying basically this. I think it's basically the same idea. Yeah. And then and we have a compliment. Yeah, you're welcome, and this is why we do it, because we think it's useful. And another compliment: my favorite show of the week. So thank you for all these compliments. Okay, so I think it was a very fruitful episode. We had almost 2,000 people actually watching the show. That is amazing. And we will be here next week again, and we are going to continue to explore Bitcoin.
Thank you, everyone, for joining this week.
Thank you. Bye, guys. Bye, everybody. Good night. Oh, and good day.